Well, thanks very much for asking me to speak today. I appreciate that. I call this presentation where there's muck, there's brass, because we're looking at muck, and brass is 30% zinc, so it seems like a very appropriate title. I was on company name would suggest we're very much in the zinc business. And zinc is mostly used in galvanizing, where it basically coats steel, about 60% of it is used in that, and stops steel corroding and therefore prolongs the life of steel products. But at the end of the day, they all end their life, and when they do, it's usually on the steel that is on a steel product, which is then recycled for the steel. And this slide attempts to show what we do in one slide. And what we do is take a waste from the recycling of steel. That produces the steel itself, a slag, and a flue dust. We get that for free, and we put it into our recycling plant. And we produce a very high-quality zinc-bearing product, which we sell back to the zinc smelters, which is rather like a mine producing a zinc concentrate, and that's 90% of our revenue. And everything else goes into an iron-bearing product, which accounts for about 10% of revenue, and we sell that back to the steel mills that gave us the dust in the first place. This employs a game-changing technology. It allows us to take the waste for free without being paid to take it away. So, if you like, redefines the material. We believe we can roll this out around the world, and the first place we're developing one of these plants is in South Korea. This is a plant which is about 3/4 of the way through development. It should be in production in the first quarter of next year. It's on budget, it's on schedule, and it should throw out about $31 million a year in EBITDA. So what I'm going to do is talk to you about the waste, then about the process, then we'll talk about the specifics of Korea, and then finally a slide at the end about the global rollout. Before I do that, however, a word about the company. We are very much in the zinc business, and most zinc comes from the underground mines where you mine the zinc mineral sphalerite, ZNS. And the technology for that is extremely well known. And we set ourselves up to look for the other sources of naturally occurring zinc, the so-called oxides. These all have rather different metallurgy, so in order to find a bespoke solution to their processing, you need a very experienced team of people, and we have that, about 128 years of experience from the top 4 technical people in the company. This allows you to develop game-changing technology, but we don't want some sort of black box with a lot of technical risk, because frankly the investors don't like it. We've got to raise money to develop these things at the end of the day. So we're very technology-driven, but I should say we're not a technology provider. We're not trying to sell technology to anybody. We want to use it for our own account. We were very much originally looking at things in natural resources, but now we've moved very much, in fact, entirely to urban resources. So it's all about recycling today. That's our focus, and our objective is to become the biggest zinc recycling company in the world, and the most sustainable. By which I mean the lowest cost, and by which my investors understand, quite rightly, the most profitable. We're here not to save the world, although it's a lovely thing to do. We're here to make money for investors. We have a head office in Surrey, here in England, where we run strategy, finance, corporate relationships, new business ideas. And in Belgium we have our technical team. We have regional offices in the States, Thailand, and Korea, where we're building up our workforce. And currently we're listed on AIM with a market cap of about £43 million. Okay, so what is the waste we treat? Well, about a third of the world's steel comes from the recycling of scrap in electric arc furnaces. And when you recycle it, it's a fairly simple remelting operation. There's no chemistry involved, if you like, it's just heat. And when you charge the scrap into a toe of molten steel at 1600 degrees, any moisture on the scrap evaporates explosively and takes with it particles of rust. So the off gases from these furnaces need to be carefully filtered in order to take out any particulate materials. And because the scrap is increasingly galvanized, then zinc, which is a volatile element and boils at just over 900 degrees, boils off, forms an oxide, and gets carried off into that waste stream, which is filtered out. And that dust, oh, excuse me, this is a very sensitive thing. That dust, can I get it on the screen? If I can. Let's try it in a minute. That dust contains about 28% iron and about 22% zinc. So that's 4 to 5 times richer than the average zinc ore body. So as a geologist, I thought, well, why am I looking for this stuff with all the risk associated with exploration when somebody will give me something which is 4 or 5 times more concentrated? And that's why I've spent the last 10 years of my life trying to find the best way of getting it out. I think we we now have that. Around the world, there's about 7 million tons of this dust produced from about 400 locations, which at 22% zinc would imply about 1.5 million tons of zinc contained per year in this dust, which is a bit over 10% of the world's requirements. In addition to zinc and iron, it also contains small amounts of cadmium and lead, but sufficient to make it a hazardous material. No, that's not going to work. Whoops. I hope that's going to go away in a moment. I'm looking at Nigel, hopefully. Oh, it's just on my screen, that's okay. So what happens to it? Well, the sort of default mode is to send it to landfill, because current recycling technology needs a subsidy in order to justify the development of a plant. So the current recycling technology is quite high cost. Where the cost of landfill is high, landfill effectively acts as a subsidy to a recycler. So where the cost of landfill is high in the developed world, typically you find there's a lot of recycling. In the developing world, where landfill is cheap, it mostly goes to landfill. So about half the world's dust currently goes to landfill. And my brief to my guys is quite simple. Find a way of getting the zinc out of the dust that doesn't require a subsidy, and we have half the world's dust at our disposal. And that's essentially what they've done. I've also said to them, well, I don't want some new black box. I want something that I can sell to investors. So if you can, please make it a technology, a modification of an existing technology. And again, they've managed to achieve that as well. So what is that technology? Well, I'm going to digress for a moment. 2/3 of the world's steel comes out of blast furnaces and base oxygen furnaces by taking iron ore, iron oxide, and coke, putting them together. It's an incredibly efficient, well-established technology, very energy efficient. But it also has dust coming off it. But in these cases, the dust contain about 50% iron and typically about 2% zinc. So most of the value is in the iron. Now you'd think with iron oxide you could just put it back into the blast furnace and reduce it again. Well, one of the problems is that it's a dust, and blast furnaces hate dust. But a much bigger problem is that the zinc is a poison. And if you put zinc into a blast furnace, it won't just make it difficult, it will ruin the process in a matter of time, over some period. So 15 years ago, obviously, landfill got more and more expensive. So the mills that were landfilling obviously didn't see that as a very long-term solution. And also, the iron units themselves became more expensive. Iron ore prices have more than doubled in the last 10 years. And here they were paying to get rid of something running 50% iron. They were having to pay to get rid of it. And then they were paying more and more to obtain feed running, say, 60% iron. So it really made no sense at all. So the rotary hearth furnace, which was a well-known piece of equipment used for heating things continuously and close to the melting point of steel, was employed and modified to work with this dust. And essentially, what it does, it is an incredibly efficient way of removing zinc. It also metallizes the iron partly, and it indurates the material, which means it hardens it so it can go back into the blast furnace. So over the last 10 years, 12 of these plants have been built around the world, mainly in the Far East. It is now an extremely well accepted iron making and dust solution to the dust problem. So if you look at the electric arc furnace dust, it's got about half as much iron in it, but 10 times as much zinc. So here we have a situation where now the zinc is the most valuable material. And you can put it into the rotary hearth furnace as it's been configured by the blast furnace operators. But the problem is that the zinc, together with chlorides that you find in the electric arc furnace dust, will in about 24 hours completely clog up the gas handling system. The quality of the zinc product is so low you can barely sell it. And remember, it doesn't matter what the zinc product quality is, because it's not a product, it's a poison in the case of the blast furnace operators. So it's a different mentality. When you change the quantity of zinc, it becomes a product, not a problem. And finally, it's very energy inefficient. So people had tried and failed to do this in the mid-90s before anybody had made it work for iron, and we were rather prejudiced against it as a technology until in the about 2006, it was obvious that a number of these plants had worked successfully in the iron application. So basically what we've done is we've broken down the process at every stage and said, how can we optimize the zinc? And this has worked extremely well. We get very high zinc recovery. We end up with an iron product we can sell because we metallize the iron. And so basically, we don't so much produce the zinc as we split the material and end up with two products we can sell, which is obviously the perfect solution. So we've taken a hazardous waste and we have destroyed it. And the net effect of this greater revenue, greater energy efficiency, higher zinc revenue is we don't need a subsidy to justify development. What do we actually do? Well, the dust is like a brown cement. We mix it with finely pulverized coal and a binder. And we push that into something that looks like a barbecue briquette. And we then dry that, and in drying it, it sets off the binder and it hardens it. We then screen that and we put a nice, clean, perfect briquette into the rotary hearth furnace. The better the quality of the briquette, the better our reactions, the greater energy efficiency we have. And the rotary hearth furnace is, if you like, a conveyor belt that works at something close to the melting point of steel, at which point steel usually becomes wobbly. So it's specially designed to be protected by refractory bricks. And it's a 30-meter diameter circular tunnel. The sides and roof of the tunnel are fixed, and the floor, which is an annular shape, rotates. And simply you put the briquettes on at one side, allow them to rotate around on the floor, and just pulling it at the beginning, 16 minutes later, you evacuate them with an auger, which is placed across the hearth base. And what happens is that the iron oxide and zinc oxide are both reduced back to their metallic form. The zinc then boils off because we're working at 1300 degrees, and in the upper part of the furnace we inject air, preheated air, which reacts with the zinc to form zinc oxide, giving an awful lot of energy, which stays in the furnace where you need it to create a good energy efficiency, and then it gets carried off in the gas stream as a very nice, clean, white product, which can be sold to the zinc smelters. What's left behind, if you like, you put on a plum and you end up with a prune. It's desiccated, it's lost on about 50% of its mass, and you squeeze that through another set of briquetting presses into a larger briquette, which we can sell back to the steel mills that gave us the dust in the first place. So because we've metallized the iron, and that's about 50% iron, of which 85% is metallic iron, it's a simple remelting operation to recover the iron. And the lovely thing about the process, of course, is, as you've probably gathered, there is no waste. So when we go to see environmental agencies about permitting, when we tell them what we're doing, they get pretty supportive and excited.